So we have seen basis dimension of a vector space, and then we have defined the row space of a matrix. Also, you can write column space. So what was that? If we given matrix A11, A12, and A1, A21, A22, A2, and AM1. So if it has m rows, okay, and 8 columns, then we have seen the span of the row space is actually the span of this R1, this one, R2, this one, and Rn. Similarly, column space is span of C1, C2, and Cn. Okay. The rank of the matrix A is the dimension of the row space, or the column space. Dimension of the column space. Now, this is not the only definition of rank of a matrix. Okay. Without introducing the vector space concept, one can define the rank of a matrix as, okay, the rank of a matrix A is the number of independent rows, or columns. Okay. Of the matrix. Okay. That is one definition. Another definition we have already seen, that the rank of the dimension of the row space or the column space. Because there is one theorem is there, that row rank of a matrix, okay, row rank of a matrix is equals to column rank of a. So those two are same. So we'll talk about only one at a time. So either a row, number of rows, independent rows, or the number of independent columns. That is a row. Okay. Now there will be another more than one definition for there, which are equivalent. From there we can have. So the rank of a matrix, rank of A is the number of non-zero rows in the row echelon form of A. Now there is a new term called row echelon form. Okay. Row echelon form. So we'll discuss this in detail after some time. But before that, we have to go back and recall that there are three type of row operations are there. Okay. So for a given matrix A, okay, we are writing the row 1, row 2, and row n. Okay. The following operations on A are called elementary row operations. Okay. There are three elementary row operations. That is row interchange. Okay, we exchange and we write this as Ri is exchanged with Rj. Okay. There is second row operation is there, that is called row scaling. We will multiply a row by a constant, a scalar. Okay. A non-zero scalar. Suppose k is a non-zero scalar. Okay. Then we will scale the function. If k is negative, then it will be reduced. If k is a fraction, then it will be reduced. If k is positive, then it will be positive scaling will be there. Negative scaling, positive scaling. So this event is represented as this one. Ri is replaced with ai. And the third row elementary operation is there. That is row addition. We replace a particular j, rj, okay, by the sum of a multiple ki, k into ri of the row I and itself. So this means that we are replacing the jth row, okay, with this new end. We are adding one row and we are replacing. So if we take one example, just we are here exchanging. So it will be, we are interchanging these two things. So it will be like, okay, R1 is replaced with R3. So it will be, so 0, 5, 9, minus 1. And then we are not touching the second row, so it will be same. Then R3 is replaced with R1. 9, 8. Okay. These two matrices are called row equivalent. If, okay, we call it B1. Okay. B1 and B1 is a row equivalent matrix. Okay, B1 is row equivalent matrix of A is row equivalent to A1 if V1 is uh, obtained by a finite number of row operations, elementary row operations. There are three elementary row operations. Finite number of elementary row operations. So that is okay. Now, if we do this, the second one, if we multiply, then the matrix will be we are scaling the function at the second row. So it will be 3, 1, 7. So we are scaling, we are multiplying with 5. So it will be 5 times 5, 5 times 1, 5 times 8 is 40, and this is 25, and 4, 1, and 3. Similarly, if we apply the row addition elementary operation, then it will be so what we are doing? We are doing with R4. 1, 0, 0, 1, 1, 1. So we are not touching others. Okay. 1, 1, 2, 3, 4. And finally, what we are doing? We are adding 4 R2. We are multiplying the R2 second row with 4, and we are adding it to the R4. So it will be like 5 plus 0 is 0. 5 plus 0 is 5. 4 plus 0 is again 4. And 3 plus 4, that is 7. Then 2 plus 4, it is 6. And 1 plus 4, it will be 5. Okay. So these two matrices are row equivalent. These two matrices are row equivalent. The same operations can be done if we have done through column operations. So elementary column operations is analogous to the same. We can do the same thing for columns also. Okay, so that is already done. Row equivalent matrix, it is already defined. Now every matrix is a row equivalent to itself. And if A is a row equivalent to B, then B is row equivalent to A. Similarly, if A is row equivalent to B and B is row equivalent to C, then A is row equivalent to C. So row equivalence we will denote by this symbol. A is row equivalent to B and B is row equivalent to C. Okay. This is equivalence symbol, equivalence. Okay. For column equivalence also we will reuse the same notation. So it will be A is equivalent to row equivalent to C. Okay. Now with these notations we are going to introduce one new definition. It is called row echelon form of a matrix, or a matrix is in its row echelon form if it satisfies these two conditions, P1 and P2, these two properties, property 1 and property 2. So property 1 says all the 0 rows. Now what is a 0 row? If a matrix has, okay, suppose a matrix has A11, A12, A1, 3, and so on. Okay. If any one of them, if a particular row is all zero, then we call it a zero row. Zero row. If at least one is non-zero, okay, if at least one is non-zero, then it is a non-zero row. It's a non-zero row. So what it says, if at all exists all zero rows are at the bottom of the matrix. It will be bottom of the matrix. Okay. And each leading non-zero entry, what is the leading non-zero entry? We'll try. The first non-zero entry in a row is to the right, of the leading non-zero entry in the previous row. Okay. So let us see some example. So let us check the property 1. All zero rows. So there is no non-zero, there is no zero row. So we don't have to check the property 1. If exists, remember if any, it is not that a row echelon form will always have a zero row. So if any, if it exists, then it will have in the bottom. Okay, now come back to the second property. Property 2 says that each leading non-zero entry, in the row 1, okay, the row 1, the leading non-zero entry is 1. Okay. The second, since it does not have any previous row, so we do not bother about whether it is right or wrong, or right or left. Okay. So in the next row, in the row 2, what we see in the next row, we have to check the leading row whether it is in the right or left. Okay. The 5 is in the right of the previous pivot. This is the leading what is it? Leading non-zero, sometimes called pivot. Okay, leading non-zero entry of the row, sometimes called pivot. Now this is our 5. Okay. Now in the third row, it is if 9 was there, then it has also be like but it is also again it is in the right. The next leading row, next leading non-zero entry again in the right. Suppose 5 was there. In case of this 5, suppose in place of here it is 0 and this was 5. Okay, so this should not be in such case it would not have been a row echelon form. Okay, so let us see another example. Okay, now we check the first property. Property 1, there is a zero row, so it should come at the bottom, and we say we check the non-zero entry. It is done. So in the next non-zero leading entry should be right to the previous one. So it is in the right. Okay. In the same way, we can have 2 zero rows. All zero rows will be at the bottom. Okay. So this is another row echelon form. So this is a leading row, and the next leading row is right to the previous one. Okay. So this is how we define a row echelon matrix. Now there are some results that can be stated, and after stating these properties and results, we will go how to solve, how to get the row echelon form for any given matrix. Okay, the thing is, Suppose the first row entry, A11 entry is 0. Okay. Then what can we do for the to find out the first leading non-zero entry? What we can say? We can interchange the first row with some other non-zero row to make the 1 1 position as non-zero. Okay. Then using elementary row operations, we reduce the matrix to its row echelon form. Okay. Now, if you think about the columns, then it can be the elements of the first column below. Okay, below the matrix. Suppose A11 is there, matrix. All the matrices will supposed to be 0 in the row echelon form, are made to be 0. Then the elements in the second column below A22 will make them 0 by elementary row operations, and in this way we'll proceed. Similarly, we can define column echelon matrices. Okay, same thing. If we do column operations, then we'll get the zeros here. Okay, we'll get zeros here in this place. Okay, this will be non-negative, non-zero, and zeros will come the upper triangle. Okay, now the fourth property says if A is a square matrix, okay, then the row echelon form is an upper triangular matrix actually. Okay, and the column echelon matrix is actually lower triangular matrix. Whatever I said just now, that if it is a square matrix, okay, then the zeros will be here and for row operation, and for the other case it will be zeros. This non-zeros will be here. So these are non-zeros. Okay. Now this row echelon form has a beautiful application to verify whether a given set of vectors are linearly independent or not. Okay. So how to do it? The given set of vectors are written in the row of a matrix. Okay. Then we reduce it to either row echelon form or column echelon form, and then check whether it has how many zeros. Okay, if the row echelon form has no zero row, okay, then we will call it a linearly independent. Otherwise, they will be linearly dependent. Okay, the number of non-zero rows. Okay, the number of non-zero rows is the dimension of the row space of the given set of vectors. Okay, and the vectors consisting of non-zero rows is the basis. Okay, let us see. Okay, let us see the first example. So the matrix is given as A. Suppose we call it a A matrix. This is B. So what we do? We are supposed to keep it as it is. First row we do not touch it now. 1 3 5. The first leading non-zero entry is 1. What we want? We want 0 here and 0 here. Okay, so how do we do that? we will use this row operation. So what we are doing actually, R2 is replaced with R2 minus 2R1. Okay. So what we are getting? So R1 is 2. So here it will give 2 minus 2. So here that means it will be 0. And the next is minus 1 and minus 6. So that means minus 1 minus 6. So minus 7. So 4 minus, this will be 4 minus 10. So this should be minus 6. And we do not touch it. The next, we'll keep it as it is. Okay. 2 minus 2, 8 and 2. Okay. Now what we want? We want in the next step, we want 1 is there, 3, 5. So we got 1, 0 here. Now we want the next entry here also 0. Okay. So how do we do that? This can be done using, we replace R3. How? If we add these two. Okay. So R3 plus 2 into R1. So this will be 0. And then 8 plus 6. Minus 7 is there, minus 6 is there. Okay. So 8 plus 6. Okay. 3 into 2, that is 6. So 8 plus 6 is 14 here. Similarly, 2 plus 5 into 2, that is 10. So it will be 2 plus 10 is 12. Okay. Now what we want? After A11 is done, the first column is complete. Okay, once it is done, we'll come back to A22. Okay, so we'll make it 0 also. So how do we do that? We can do it by replacing the R3 as R3 plus 2 into R2. So it will become 1, 3, 5, 0, minus 7, minus 6, and 0. So 14 minus 14 plus minus 14. So it will be 0. 12 plus minus 12. So again it will be 0. So here we are getting 1 0 row. So this is not linearly independent. In other words, okay. Now we check whether we have arrived to the row echelon form or not. Whether it is row echelon form, if you check the first property, yes, the 0 row is in the bottom. Check the second property. The leading non-zero entries are right to the previous one. Okay, so property 1 is satisfied. Property 2 is also satisfied. So we can call it, this B is the row echelon form of the given matrix A. Okay.
Sir, excuse me, sir.
Yes, yes, tell.
Can you explain that second property again, sir? I did not know.
Okay, I will explain of course. Just a minute. Okay, let us go back. Second property. Second property says each leading non-zero entry in a row is to the right of the leading non-zero entry in the previous row. Okay, so what it means is actually, okay, so if you consider about this matrix, look at this matrix. So this is our first non-zero. Suppose this is non-zero. Okay, since it does not have any previous row, so we'll keep it as it is. Okay. Now what we know, what we have to check? We have to check the second. Suppose this. Okay. Let us see the example. Yeah, here. Look at these examples. The first non-zero, the first row we do not bother about. If A11 is non-zero, the leading, okay, leading coefficient, leading entry is non-zero, then we don't have to bother about it because it does not have any previous row. Okay. Then the next non-zero leading row, sorry, non-zero entry in the next row in the row 2. Okay, 3 is there also. And this is right? 3 is actually right of this previous one, previous row. Okay, previous non-zero entry, leading non-zero entry. So it 3 could also be here also. Okay, then also it is low echelon form. But in for particular example, we may get 0 here, but we can get 1 here. I mean non-zero here. So that is also. So is your doubt clear now?
So then the first property itself satisfies the second property now, sir. Then why to go for second?
No. So the first property says all zero rows, if it has a zero row, say non-zero, here all the 3 rows are non-zero. Okay, what is a zero row? I have defined here. Okay, if it has all zeros, zero entry in a row, then it is zero row. If it has okay, if it has a non-zero row, I mean all the zero rows will be at the bottom. See in the third example, we are having just a minute. Yes, where were we? So, okay. The first property says all the zero rows will be in the bottom. Okay. The second property says each leading non-zero rows is in the right of the previous row. Okay. So this does not imply the each of them. This is different property and this is also different property.
Okay, sir. Understood, sir. Thank you.
Okay.
Sir,
Yes, tell.
sir, what does remark to tells us? Means what is the application of remark to?
Okay, remark 2.
Yes, sir.
Remark 2 is just a property. It does not have any application.
Okay, sir.
Sir,
Okay.
I didn't understand remark 5.
Okay. Remark 5. Remark 5 says if, okay, it will be clear if we do some more examples. Okay. Earlier we have suppose V1, V2, and V3 are given. A set of vectors is given. Okay. Now the question is it linearly dependent or linearly independent? Okay. If the question is like that, so then we have seen that we have to take the linear combination C1 V1 plus C2 V2 plus C3 B3 equals to 0, and from there we have to check whether all are non-zero or all are 0. If all are 0, then we call it linearly independent. Okay, and if at least one is non-zero, then we call it linearly dependent. Remember? Okay.
Yes, sir.
Okay. Now another property is there. We have checked that if we take the determinant, okay, determinant of V1, V2, and V3. Okay, so like this one, some non-zero, some vectors are okay. What we have seen, if the determinant is non-zero, then what will happen? Yeah, if it is non-zero, then we have said that it is these vectors are linearly independent. Remember, if it is 0, then it is dependent. Okay. So the same thing is happening. Now, if you look at the this row echelon form, okay. Now, if you take this determinant, what will happen? So one row is 0, so determinant will be 0. So it implies linearly dependent. Okay. So these three vectors are linearly independent. Since a row, in the last class I have said that a row is a row. Sometimes we call it a row vector. It can be treated as a vector. Row vector. Okay.
Sir,
Yes.
sir, the property 1 of REF says that we must have all 0 rows, which means all 0 elements in a row. And it must be in
No,
the
no,
bottom
no.
of the row.
Property one says if at all exist, if exist a 0, then it will be in the bottom. Okay.
Yes, sir.
Look at the three examples. This is also a row echelon form. All the three are row echelon form, but all the it does not have any 0 row. Okay, so you don't have to bother about it.
Yes, sir.
If exist, remember, if exist,
Yes, sir.
if any. Note that the language is very important. Okay. So if we look back, if we go back,
Excuse me, sir.
yes,
Sir, in example 1, in place of first operation, can we use R2 plus R1? R2 plus R3?
R2 plus R3 in the here,
Yes, sir. We can get a 0 in the second
R2 plus
row.
R3.
Or,
Yeah, you can
yes,
do
sir.
it by anyhow. What is it? R2 plus R3. Yes, you can do it to make it 0. Yeah, you can do it. No problem in that. But anyhow, you have to satisfy those properties. Okay. You have to bring
Yes.
1 0 0. Okay. All the rest of the things you have to make it 0. Okay. There is no burden that you have to only use this one. But it has been proven that if you select the pivot element, it will help us to make others 0 in a convenient way. So now remember the definition of rank. So the rank of A, the given matrix A, will be number of non-zero rows in the echelon form. So here it is 2 only. So 2 non-zero rows are there in the echelon form. So the rank of A is 2. Okay. That means if you take the row space from here, we will get a row space, a column space. Okay. Row space will be a span of row space of A. Okay, will be the span of these two vectors 1 3 5 and 0, -7, -6. So these two vectors. The dimension of this row space will be 2. That is, rank of the matrix is 2 actually. Okay. For matrix, we will use rank. For matrix, we use rank. Okay. And for vector space, we use dimension. Okay. So we move forward to see another example. That is B. Whether it is row echelon matrix or not, we have to check. I mean, we have to verify. We have to find the row echelon form of B. Okay. So how do we do that? Let us move. So it can be. So if you are confident in row operations, okay. Earlier we have seen one by one. So if you are confident, you can do all three operations in the first step only. In a single step, you can make it. So first non-zero is 1. Okay. In order to make the second row as 0, then what we have to do? That R2 minus 2 into R1. Okay. In the third entry, in the third row, if you want a 0 here, then we have to subtract R1 from R3. Similarly, we want 0 here, so we will subtract the first row from R4 and we will multiply the first row with 8. Okay. So in the next step, in a single step, we will get these operations. Okay. So if you are confident in row operations, so you can do one step also, all the operations. So once we get zeros here, okay, now we go to A22. A22, this is A11, is done. Now we want 0 here. So we'll do it again here. But our target is to make this one 0. Okay. This may be some other entries. Will at this present stage we will be focusing on making these entries as 0. Okay, if others become 0, then we are no problem. Then we have no problem. So here what we are seeing here that there are two zero rows. Okay, since the number of non-zero rows of this matrix, suppose this is called B matrix. So rank of B is equal to 2. Okay, so this is how we will find out the row echelon form of any given matrix. Yes. Now we see some more examples. Examine whether the following set of vectors is linearly independent or not. Okay. Find the dimension of the basis of the given vectors. Okay. You have to find the dimension of the basis. Now also in the row echelon form, whatever the non-zero rows we will find, okay, whatever the non-zero rows, these non-zero rows will be linearly independent. It can be proven if you check independent. These non-zero rows in a row echelon form are linearly independent. Okay. You can check also, you can verify by definition. Okay. You have to take C1 into 1, 2, 3, 4 plus C2 into 0, -3. Okay. 0 minus 3 minus 2 minus 3, make it 0, and from here you will get C1 and C2 as 0. You can verify also as a task. So the next 3 examples are there. Okay, a given set is S1. Okay. Okay, the vectors are, this is actually 4-dimensional space. Okay, subset of R4. Okay, and this is also a subset of R4. This is 1, 2, 3, 4, 5. So this is subset of R5. Now, in order to verify this set is linearly independent or not, what we do? We take these vectors as a row of a matrix, and we find out the row echelon form. Okay, so we have written this matrix as the given vectors are written as a row. We apply the row operations. Okay, now we find out that it has a 1, 0 row. Okay, so the row rank. Okay, so the rank will be only 2 non-zero rows there. Okay, now if you consider the row space is actually span of these two vectors 1, 2, 3, 4 and 0 minus 4 minus 5 minus 10. Okay, these two vectors, and we have seen that they are linearly independent also. Okay, you can see them, you can show them, they are linearly independent. So the row space, okay, dimension is rank 2, so dimension of the vectors corresponding dimension is, dimension of this row is, row space is 2. Okay, and this is nothing but the basis actually. Okay, this is a basis for this row space. This will be a basis for this row space. Okay. Similarly, if we look back, if we move forward for the second example, then what we see, we do the row operations again for the matrix. Okay, and we check the row echelon form, of the given matrix A. So here we can see that there is no zero rows, so it will have, so these 4 vectors. Okay, so the rank of this particular matrix, this rank will be 4. Rank will be 4. Rank of A, this matrix, is 4. The corresponding row space, okay, the row space will be the span of these 4 vectors, span of these 4 vectors 1, 1, 0, 1, then 0, 2, 1, 2, and then 0, 0, 1, 0, and 0, 0, 0, 1. Okay. Then the dimension of this row space is, actually 4, and it will be, this vector will form a basis. These 4 vectors, okay, will form a basis for this vector space, this row space. Okay, So this is how we'll apply the concept of row echelon form to find out the rank of a matrix. Okay. Similarly, in the third example, okay, we will see there is a row. There is a zero row. Okay, so the rank of only we have two non-zero rows, so rank of the matrix is 2. And the basis for the row space will be the span of these two vectors. Sorry, this is a basis actually for this row space. Okay. Now, I will give you some practice problems and I will stop here today. So if you have a couple of doubts, I can answer. Actually, while I am presenting, I am not able to